Nuclear energy. Now, what is nuclear energy, you may be thinking? Nuclear energy is the energy released during nuclear fission or fusion, especially when used to generate electricity. Understand? I thought so. Fuel in nuclear power stations is uranium, and the uranium is sealed in cans in the core of the reactor. As the nucleus of an uranium atom splits into two when a neutron from the outside, the atom collides with it, therefore energy is released. The process is called nuclear fission. Now, what is nuclear fission, you might ask? Well, this video explains it all.
Atoms are very small, but there are two ways we can get enormous amounts of energy out of them. These are nuclear fission and nuclear fusion. Nuclear fission powers electricity generators. Okay, but nuclear fusion powers the sun. Fusion wins. But first, we'll look at nuclear fission. This means splitting atomic nuclei into smaller pieces. But not just any old atom will do. We need big ones. Uranium and plutonium are the business. Either of these can be used as fuel in nuclear reactors. In fact, particular isotopes of these elements work best. They are uranium-235 and plutonium-239. They both have large nuclei that split easily when we hit them with neutrons. Let's have a look at chain reactions. First, we need some nuclear fuel. We'll use this uranium. To start things off, you fire some neutrons into your lump of uranium. When a neutron hits a uranium nucleus, it splits into two pieces. This releases a lot of energy. And it also frees 2 or 3 more neutrons in the process that zoom off at high speed. If they hit other uranium nuclei, they'll split them too, and so on. Each split sets off more and more reactions. This is called a chain reaction. Things could get a little out of hand, as you can imagine. Nuclear power stations use chain reactions just like this. Yeah, that is a bit scary. Of course, the rate of the reaction is carefully monitored and controlled with control rods that absorb some of the neutrons. This means the chain reaction goes along at a steady pace, otherwise the whole thing could snowball and it'd be curtains.
What is inside a fission reactor, you may be wondering? Neutrons can cause other uranium nuclei to undergo fission. Then, a chain reaction can occur in the core of the reactor. When lots of uranium atoms are in the core, it becomes very hot. Thermal energy of the core is taken away by a coolant that pumps through the core. The coolant becomes very hot when it leaves the core, and as it flows through a pipe to a heat exchanger, it will then flow back to the reactor core. The heat or thermal energy of the coolant is used to convert water into steam in the heat exchanger. The steam drives the turbines, which turn electricity generators. And this is what a fission reactor looks like. This is what goes on inside the reactor.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the brink of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of 3 crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reaction.
Moving on. Now for nuclear fusion. The sun and stars release energy and resulted of fusing small nuclei to form larger nuclei. When two small nuclei released energy and fused together, they can form a single larger nucleus. The process is called nuclear fusion. Here is a video on nuclear fusion and what happens inside a nuclear fusion reactor.
Nuclear fusion, the other type of nuclear reaction. Here's the sun. It's really hot apparently. The enormous amount of energy the sun produces is created by nuclear fusion. Fusion is the opposite of fission. Fusion is about joining atomic nuclei together, not splitting them apart. Here we've got two hydrogen isotopes. Hydrogen 1 is just the usual type of hydrogen. But notice the surprise appearance of a neutron in hydrogen 2. In a fusion reaction, these hydrogen nuclei join to form helium nucleus. In fact, it's a helium-3 nucleus, not the usual isotopes of helium-4 which has 2 neutrons. In symbols we write it like this. We include the mass number and the atomic number for each atom so we can see exactly what is going on. The mass number is the total mass of the nucleus. That's protons plus neutrons. The atomic number is just the number of protons. Fusion reactions release enormous amounts of energy, much more than feeble old nuclear reactors and nuclear bombs. So it'd be a great source of energy for us humans. But no one has found a cheap, practical way to get fusion working yet, which is a shame. Nature can manage it though. All the stars, including the Sun, are massive balls of fusion reactions. They release enormous amounts of energy, including light and heat, that reaches us here on Earth. Free energy! Great! But is this sustainable? Well, no, but don't worry. The Sun won't be running out of hydrogen for quite a while. That's going to take a few more billion years. So don't change your holiday plans just yet.